2.3 Example solutions of the Schroedinger equation. Previously, we learned the Broglie hypothesis, where energy is equal to h bar omega and momentum p is equal to h bar k. And we know that in particle picture, energy E is the summation of kinetic energy T and potential energy V. And this can be also represented like P squared over 2m, where P is that momentum, and then V represented in spatial coordinate. Momentum P in particle picture is written as m and then v, the velocity of the particle. So two concepts are correlated now. The wave picture and particle picture, they are correlated. And in the description of waves, we found out there is uncertainty relation, where the space uncertainty, position uncertainty delta x multiplied by momentum uncertainty delta p is no less than h bar over 2. There was expectation values. For example, let's consider average value of A, which is defined mathematically as shown here. The denominator is supposed to be 1. This is the definition of wave function. And wave function square is the concept of probability. Probability. More exactly, probability to find a particle at certain position r, that is psi r, or psi x in one-dimensional case. So this class we will rather focus on one-dimensional case. 3D and 1D. Sometimes when the wave function structure is too complicated, it is very hard to set it to be normalized. Then we need to go through this additional process in the denominator. And here, numerator, we are calculating that average value of A. So A cap is the operator to induce A, then psi. Then we multiply them by psi star. So considering the conventional definition of normalization, and this is just the same with this one. The denominator is set to be 1. This is what we studied previously. So over the last class, based on the Broglie hypothesis, we could induce the Hamiltonian operator or energy operator, which means if you take this H cap on psi, then we will have energy psi. Today we will practice solving simple problems based on this equation. So these are on the basis of textbook chapter 2.3. Free particles. A free particle is one that it is not subject to any potential constraint. That is, potential energy U, or sometimes V, is equal to 0. We can think of this free particle as a free electron. In particular, we are interested in the case of electron in semiconductors for applications. In the case, if it is free, it means this electron is not under Coulomb attraction anymore, Coulomb attraction or Coulomb repulsion. And we call it sometimes vacuum state. We call that electron is in the vacuum state. For a particle traveling along x direction, SE Schroedinger equation becomes this one. This is what we discussed previously. This is called time independent Schroedinger equation. So this is the operator corresponding to kinetic energy, and then there is potential energy part, which is set to be 0. Then previous equation is simplified like this. The solution of the above equation is this one. This is actually very simple second order differential equation. And when we solve these equations, we arrange it like this way. D square psi dx square equal to energy psi, and then this one is equal to minus h bar square 2m e psi, and we set this to be k square, so that it becomes minus k square psi. Sometimes this left hand side is indicated by psi double prime. When we solve this two second order differential equation, so the idea is you take the second derivative and you have original equation multiplied by something else. It has negative sign here, so the general solution could be this one, or sometimes you can set it to be a cosine kx plus b sine kx, because both cosine and sine functions, these two minus k square, under the second derivative operation. And then most general solution is shown this way. We take them with certain weighting factor here, a and b, and then we decide a, b, and k. Likewise, exponential function also has the same result. Take the second derivative, then we have minus k square. So it has either minus sign here or plus sign. Both of them will have same form. And then the most general solution is shown here. This is actually what we learned from differential equation classes. And the energy was defined here. So k square was 2me h bar square. So we take the square root on both sides. It will be like this. That definition is here. The time dependent wave function is then found to be the subscript t indicate time dependent, then original time independent wave function multiplied by e to the minus I omega t. Surely omega is equal to e divided by h bar. Then it is like this. Here we see that, let me erase a little bit here. Okay. The first term represents a free particle traveling in the negative x direction, because when t becomes larger, x should be smaller, should become smaller. So it is traveling in the negative x direction. This one, second term, propagates along the positive x direction, because as t increases, x should increases to have the same exponent or phase. Quantum mechanics consider this phase to be very crucial or important. In conventional mathematical formulation, we call this as the exponent, and in quantum mechanics we call it phase. When you also have cosine or sine function, for example in cosine function, like this way, cosine kx minus omega t, then within this parenthesis we call them as a phase. But as you can see, x and t, they are independent variables when you have that kind of independent variables, they are not fixed anymore, they are changing. But if we have additional value which is not changing, like this one, then in that case we call this pi as phase. Okay. Alright. So when things are not defined within this parenthesis, we call them as a phase. But when we know, okay, x is the position, t is the time, and they are independent variables, then we rather call this constant value as a phase. And we consider this phase to be very important in quantum mechanics because we need to care about wave properties. And wave properties are dependent on the phase. When we consider the superposition between different waves, okay, we will discuss these concepts many times. If you have additional wave which has different phase, when they have a different phase and then we sum them up, this is something called superposition in mathematics. And depending on the difference between pi prime and pi, we might have constructive interference, destructive interference. That's very important in wave description. So that's why I'm talking about this value within parentheses. Anyway, let me erase this part for now. Okay. In terms of Heisenberg uncertainty principle, equation 2.34 shows that wave function for a right traveling wave extends from x equal to minus infinity to x equal to infinity with equal probability everywhere, which means that its position is not determined at all. Therefore, the wave has the fixed momentum defined by k. So this is very simple to follow, but has important meaning. Look at this, the probability. Because the wave function is spread over x space with equal probability everywhere. I mean, as a function of x, if we consider the psi and then psi prime, multiply them, that is the probability, then it's always the same. Okay. So especially when you consider the right traveling wave of this part, then when you take the right traveling wave, you have psi conjugate and then psi, take the absolute value, take the square, what we have is b square. Okay. It is just the same. Wherever you are, wherever the electron is located. So it is called as equal probability everywhere, which means the position is not determined at all. Then it means delta x is infinity. And delta x delta P is supposed to be no less than h bar over 2. This is finite. This is infinity, right? Then delta P should be 0. Delta P is 0. It means momentum P is fixed. Momentum P is fixed. Fixed at K. So that's why we have definite value of K. Similarly, the wave has fixed energy defined by omega, but spans time from negative infinity to positive infinity. So what does it mean? I mean, delta E, because energy is fixed, delta E is 0. And in time scale, it spans from negative infinity to positive infinity. So delta T becomes infinity. Thus, the Heisenberg uncertainty principle holds true for this simple case. Particle in a one-dimensional potential well. We consider the case of a particle in one-dimensional potential well, which can be, for example, an electron subject to an electric potential field. In other words, electron is confined within potential well, as shown in figure 2.5a. This one. A particle of mass m confined in a one-dimensional box of length d. So length d. For the particle to be confined within region 2, the region 2. So confined region is named as 2. The potential energy outside regions 1 and 3 is assumed to be infinite. So here the potential is presumed to be infinity here in region 1, infinity in region 3, and set to be 0 in region 2. Okay. And this is often found in semiconductor structures, because if we have certain structure with smaller band gap, okay, then surely you have conduction band and valence band, okay, and their separation is band gap of smaller band gap site, and then there comes larger band gap material, okay, and it is often called as barrier with large band gap. Many of the semiconductor structures consist of this quantum well barrier combination. Quantum well could be, for example, gallium arsenide with lower band gap, and barrier could be, for example, aluminum arsenide. Such structures are well defined in terms of growth, so we can make these materials in systematic ways. Gallium arsenide band gap such as 1.4, aluminum arsenide band gap at least larger than 2 electron volt. Then carriers will be accumulated in lower band gap side, gallium arsenide side. So structure is actually conduction band we have, valence band we have. But here, for simplicity, let's ignore this part for now. Okay, we only consider conduction band for now, and let's set the minimum energy of the electron to be 0. Okay, so based on this minimum energy, which is set to be 0, we consider the energy of the electron. Okay, and then we will extend this structure into the case of realistic semiconductors later on. It's not that difficult to extend. The most important part is we want to calculate the energy of the confined electrons within quantum well. So quantum well barrier issue was explained. It is actually the small portion of conduction band, valence band structure. And now let me remove this, erase this part. Okay, good. So in the case of figure B, particle energy quantization in the box and wave function for the first 3 levels. So this solid line shows the wave function with certain offset. Okay, so this is energy value, we call it E1, another energy value E2, and another energy value E3. And wave function is supposed to be normalized. So we have first wave function here, and second wave function, this one. This is not the unit of wave function. We are just showing the structure of wave function, not the exact value. This offset is not related to wave function. It is only indicating the energy state, energy values. And then this is the wave function for the third state. The strategy for obtaining the energy and wave function is that we solve Schroedinger equation in different regions. Surely the easiest, the first. Then apply the boundary conditions. So we have 3 different regions, and here the potential is set to be 0. In this equation, time independent Schroedinger equation, we set this to be 0 and solve the second order differential equation. This is the same with the free particle case. We know the solution. This leads to the same solution with the case of free particle. This one, because potential was set to be 0, and then we divide both sides by minus h bar square over 2m. Then we have this one, this value. The same with minus k square, where we define k equal to square root 2me over h bar square. The general solution in region 2. Now we rather use cosine and sine combination. This is the most general solution. So we will either use cosine sine combination or exponential function like kx, ikx, or minus ikx. There should be weighting factor or some constant like this. This a and b, this a and b, they don't need to be the same, so it might be different. So we'll rather choose this one or this one. In this class, many cases we will rather use cosine and sine functions instead of this one. Okay. So the solution in region 1 and 3, wave function psi should be 0. Okay. We can think of y. For example, this one was the case of region 2. In region 1 and 3, we have here u becomes infinity, but the energy is finite, and wave function should be finite because we have constraint of normalization. So the probability is integrated and it is 1. So this is finite. So finite value, another finite value is equal to some value and then add it up with infinity multiplied by wave function. So to satisfy this condition, wave function psi should be 0. So this is the way in region 1 and region 3, wave function psi should be 0. Yeah, that's what we are indicating here. The solution in regions 1 and 3, psi is 0. Okay. So let me erase this part. Good. Okay. Then we apply the boundary condition. This is very important procedure. Every time when you calculate wave functions in different regions, there are always boundaries. For example, the intersection between region 1 and region 2, that is boundary. Or in realistic case we call it interface. Okay, interface. Interfaces or boundaries should have certain conditions, something called continuity of the wave function. Wave function should be continuous at the interface or at the boundary. For example, region 1, region 2 as the boundary at x equals 0, and region 2 and region 3 as the boundary at x equals t. Okay. At x equals 0, wave function here was always 0, and x equal d, and also in region 3 wave function is 0. So in region 1 wave function is 0. In region 2 wave function was calculated to be a cosine kx plus b sine kx, and we plug x value into here, right? They are continuous, wave function is continuous, so region 1 and region 2 wave function value should be the same. We found our sine kx should be 0, cosine kx, and x is 0, then this should be 1. So 0 equal to a, so a should be 0. It means this part now removed, so wave function psi x is equal to b sine kx. Also for x equal d, psi d should be 0, so we put d into here, then b sine kd is equal to 0. So then multiple solutions for energy exist at when kd satisfy n phi. Now n is the integers. Actually, that's the way we satisfy this condition. Yeah, that's the characteristic of sine function. And n could be actually any integers such as -1, -2, -3, and 0, and 1, 2, 3, and so on. But here we ignore the 0, we ignore negative part. So that is explained here. Here we take only positive values of n. Since the negative values give the same electron probability distribution functions and are thus identical to positive solutions, it means that wave function psi has now the structure of b sine kx. So depending on this k value here, I mean k is depending on this n, and could it be positive or negative? Then when we compare these positive versus negative values, if we put these negative values into here, okay, then it'll just induce negative sign, and everything else is just the same. Okay, so positive case, negative case, right? In terms of wave function, we have opposite sign, but in terms of probability, which take the square of absolute value of psi, then they are just the same. So we don't care whether it is plus or minus. So that's why actually this positive values and negative values of integers will lead to same probability. Okay. So in quantum mechanics, there is a convention to ignore this negative integer values. Okay, we ignore this part. Okay, right, we ignore this part from now on. The value n equals 0 is excluded, since taking this value will lead to psi equal to 0. So when n is 0, k is 0. What does it mean? K is 0. The wave function is 0. So wave function is 0, it means the particle doesn't exist, right? Because wave function square is equal to probability. The probability becomes 0. What does it mean? The particle doesn't exist, which contradicts our original postulate that there is an electron, right? There is something. So n equal 0 is excluded, since taking this value will lead to psi equal to 0, which means no particle exists inside the region. The integer n is called as quantum number, which n corresponds to a wave function and an energy level. For multidimensional problems which we will encounter later, there will be more quantum numbers. Quantum numbers along x-axis, y-axis, z-axis. And then there comes angular momentum and spin quantum number for electrons, which will be discussed later on. For equation 2.41, the allowable energy levels are now En equal to h bar square over 2m. And then what is this? This is k square. Okay, and k square is a function of n, so sometimes you can write it down like kn. N is that quantum number, varying like 1, 2, 3, and so on. Corresponding wave function of psi n is now b sine kn x. Kn is given here, right? Applying normalization condition. Now we are applying second condition. Firstly, it was boundary condition, and now normalization condition. To find the coefficient b, so we take the second derivative. So psi n multiplied by psi n conjugate, then actually this is just real function, so we multiply them. We have b square sine square kx, and wave function in region 1 and 3 are 0, so we only care in region 2, right? Then sine square is replaced by this one, right? 1 minus cosine 2kx over 2. So if we integrate from 0 to d, you will see this will be 0. Okay, you can try yourself. This will be 0. Then the rest of the integration is b square over 2 multiplied by d. And this one is 1, so b is said to be this one. Surely b could be either positive or negative value, and we only take the positive side. Okay, particle in one dimensional potential. Well, so these wave functions are standing waves, as shown in figure 2.5b. So we had 3 different wave functions. Why do we have standing waves? Because wave function is said to be 0 at the boundaries. Okay, 0 here, 0 here, 0 here, 0 here, 0 here. That's the characteristic of standing waves. The separation between successive energy levels depends on the width d, this one, because energy is said to be like this. What is the separation? The separation is also important in application. The separation is, for example, E2 minus E1 or E3 minus E1, for example. These are actually important values in practical application. Okay. For example, if the electron is located here in semiconductor materials, and then we apply certain light excitation, and then if this energy of the light is happen to be the same with E2 minus E1, sometimes this electron is excited into N2, and this process includes the absorption of light. Okay, absorption. And the energy separation between E2 minus E1 is usually on the order of like 100 million volt, or sometimes we can control that energy depending on the value of D. Okay, so this and this is actually corresponding to, for example, 2 terahertz. And this one, like on the order of 20 terahertz. Yeah, so this is the idea of terahertz absorption. Okay. And it can be also extended into terahertz modulation devices. This is the main idea, for example. So the separation between different energy levels can be useful. Okay. So well, as an example, we additionally consider the concept of the when the energy separation is larger than the thermal energy fluctuation. Thermal energy, as I said before, is on the order of like a 20 electron volt. For example, 26 electron volt is equal to K. Here K is Boltzmann constant, so let's use the subscript B, then at room temperature. Okay, so here T is like room temperature. Alright, so if this separation is like a 20 electron volt, similar to thermal energy, then it's very hard to recognize the energy separation. So that's what we are saying here. When the energy separation is larger than thermal energy fluctuation, this one, the quantization effect can be easily observed. For electrons, this requires in general, that D is smaller than 100 angstrom or 10 nanometer. This is often called quantum well width. Okay. As an example, what is the energy separation in the case of electron mass 0.067, yeah, M0. M0 is the free electron mass. Okay. M0 is free electron mass, and it is equal to 0.5 mega electron volt in CGS unit. In semiconductor devices or in general applications, we use CGS units many times instead of SI unit. And this is the case of gallium arsenide. Effective mass, we call it. The mass of electron in semiconductors, we call it effective mass. And then let's say 10 nanometer quantum well. This is conventionally available. And calculate yourself based on the energy separation. So what could it be? E2 minus E1. In this case, so try calculating yourself. This might be one of the midterm exam problems. Okay, so you calculate yourself, right? Based on the center point of the well, we also note that the first and the third wave functions are symmetric, and the second wave function is asymmetric. Okay, remove this. So center point is here actually. I'm not good enough, but you know the meaning of this. So center of the quantum well. Okay, and then there is something called symmetry. Based on the center point of the well, we also note that first and third are symmetric. Okay, from the center of the quantum well. So this side is the equal shape. Okay, then we call it symmetric. The second one, okay, not symmetric, and then we call it asymmetric. This symmetry becomes clear when we shift the origin so that x equal to d over 2 becomes 0. So let's set this to be 0 now. Okay, new origin is here, center of the quantum well. Then original wave function, this one, psi x equal to square root of 2 over d sine kx. Or this kn is now replaced by this one, m phi over d. Then this position shift by d over 2 changes original function like this, right? N phi over d, this is k value, and x is replaced by x minus d over 2, right? And this one actually becomes sine t m phi x minus D and D, 2 and 5. When n is 1, we have addition of phase of minus pi over 2. Then we change sine function into cosine, right? When n is 2, then we have additional phase of pi. Then we have same sine function. When n is 3, we have additional phase of minus 3 half by pi. Then we change this into cosine function again. Okay. So we see that cosine and then sine and cosine. We know that cosine function is called as even function. Sine function is classified as odd function, and odd function is asymmetric function. Even function is symmetric function. Okay. We note that the first and the third wave functions are even functions, while the second wave function is the odd function. Right. Let us now show that Heisenberg principle is satisfied for n equal 1. This is actually taken from the textbook of Gang Chen. The most probable position and the standard deviation in its position can be calculated. For example, the average value of x. This is the actually expectation value of x. Then so this is the most probable position. Actually, we know the wave function shape of psi 1. Okay, psi 1 was symmetric from the center of the quantum well. If it is x equals 0, if it is x equals d, the maximum amplitude of a wave function is found at the point of t over 2, and it is symmetric. So the average value of the position will be here, right? t over 2 we already know from this intuitive picture, and mathematically we go through this calculation. Okay, psi 1 star x psi 1, then we calculate this. Okay, so we put those wave function shape, then we can get that let's say 4a square 0d x sine square, and then we integrate this one. We know a value, we know this one. This one actually 2 1 minus cosine, sorry, let me do it again. Cosine 2 phi x t, right? And then we multiply by x dx. If we integrate this from 0 to d, we need to use the technique of partial integration, right? Partial integration. That's what we learned from high school mathematics classes. So if you go through that process, I think everyone can do that. So probably you do better, practice that procedures yourself, and you will get d over 2. Okay. So mathematical procedure will lead to the same value with our intuitive picture. Then this one is the standard deviation, defined this way. X minus average value of x, which is this one, and then take the square, and then we take the average value and take the square root. So this is rather complicated mathematical procedures. You need to go through this, right? So here we put this number. Actually, when you set this to be 0, okay, when you set this to be minus d over 2, and this one now becomes d over 2. If it's like that, this one will be 0, okay? So most probable position will be 0. And then this calculation will be simpler, okay? Because this can be easily this one now set to be 0, okay? Easily remove this way. Then we can calculate this one. Possibly you will have the your own calculation in homework problem set. Similarly, the most probable momentum and uncertainty standard deviation in its momentum are the most probable value of momentum. You calculate that and you will find it to be 0, okay? And standard deviation of momentum, you will calculate this one, okay? So these are actually just mathematical procedures, a little bit tedious, but anyone can do it with patience. Then this delta x and delta p, we multiply them, we'll get d and d. They subtract with each other. Then we have certain constant values. So from equation 2.47, 2.49, we obtained delta x, delta p, we multiply them, then we'll get this number, thus satisfying the Heisenberg uncertainty principle. This example shows, although the electron at n equal 1 energy level is most probably positioned in the middle of the potential and has 0 average momentum, it can also be at other locations because it has spread over the quantum L, as the wave function suggests. There is momentum uncertainty. NRK dispersion for semiconductor. This is rather realistic case. In here, carriers can move freely in YG plane. Now we consider additional YG plane movement in quantum wells when the potential U was buried along x-axis. and each quantum number corresponds to each subband for given quantized kx. Those are actually important terms for real application. Previously we have quantum confinement, where the potential is infinity in region 1 and region 3. Within quantum well, potential is 0. The position is spread from 0 to d. Okay. In this case, energy is discrete. E1, E2, and E3 we considered. E1 shown as 2m h bar square k1. E2 2m h bar square k2 square r, the square here, and k value was previously calculated to be m5 over d. D was quantum well width. Now we will extend this into three-dimensional case, so let me replace this d into a for now. A is the quantum well width. Okay, so these are energy defined along x-axis. Then how about y and z plane? They are free, so we need to add additional energy, free particle kinetic energy. Okay, it's shown here, h bar square 2m over 2m ky square. The momentum along the y-axis is h bar ky. They are free. It means ky is continuous. And this one, kz, is also continuous. So now the total energy in 3 dimensions, we need to add energy along x-axis with energy in yz plane. The energy E1, E2, we have separation. Okay. This axis could be ky or kz. Then if we draw down the curve of energy, we see that as a function of ky, it is increasing with second order. Okay, we call it parabola, right? And there's nothing in between, and then there comes minimum value E2, and we have additional parabola. So you will see this kind of energy shape many times in semiconductors. Okay. Further confinement leads to 1D, which is called as quantum wire or 0D quantum dot within the infinite barrier height approximation. So potential is presumed to be infinity. If we consider 1D, then it means carriers can move freely along 1D. That direction is actually said to be y-axis. And here, x-axis we have confinement, g-axis we have confinement. Okay, so we have quantum number along x-axis. Okay, here nx. Previously we only had n, but now we need to have three-dimensional k. So let's set to be set this to be nx. And let's say we have additional confinement along z-axis, then the z-directional quantum confinement is represented by quantum confinement quantum number nz, okay, and the scale is b. So this is b, this is a. Carriers can move freely along y-axis, so the kinetic energy of free particle moving along x-axis should be added like this way. Okay. And quantum dot case. So this is the case when carriers have zero-dimensional confinement. X-axis, now z-axis, then y-axis. So carriers are confined in a box, then the energy should be defined like this way. Energies are defined by this quantum number along x-axis, quantum number along z-axis, quantum number along y-axis. So energy now is a function of these quantum numbers. And sometimes this is called as artificial atom. Okay. The movement is 1D, right? But potential confinement is along 2D. So this is called as 2D potential box. Okay, but it is one-dimensional movement. Okay, this is zero-dimensional movement and three-dimensional potential box. And it is sometimes called as artificial box, artificial atom. Okay, and also we will consider something called degeneracy. So in the case of quantum wire, we have two-dimensional potential box. Here, let's say quantum confinement is along x and y axis and along z axis. Let's say it is free. Okay, so we need to calculate the quantum confined energy along x-axis and y-axis, right? Then in addition to quantum well problems of one-dimensional potential wells in which quantum effect occurs in the direction of semiconductor thickness, previously we solved the equation along x-axis. Now we consider like x-axis and y-axis together. Then the equation is actually extended like this way. When the potential U is 0. Okay. And this one is rather complicated because now we have two independent variables, x and y. Then the idea is we set psi to be large x by large y. This is called as separation of variables. Okay, this is the conventional method to solve complicated problems. Separation of variables. Separation of variables. Okay, so we put this into here. then psi is replaced by x and y. Right? This one is replaced by x and y. Then we have this equation. We put this into here, then this is operation on x, and this is operation on y, right? So y is separated, and we go through round square x, round x square. X is separated. We go through round square y, round y square, and then we divide both sides by x by y. Okay, x times y, we divide both sides like this way, and then we have this equation, right? Because we divide it by x and y, then we can see that this one subtract with each other, this one subtract with each other, and this one subtracted, and we only have energy E remaining. Energy is replaced by EX plus EY, because this one is a pure function of X, this one is pure function of Y, so this one is set to be EX, this one is set to be EY. Okay, and then we have two separate equations. Okay, this one is just the same with the free particle case, and we solve two independent equations, right? So Cx Ey, now considered, we consider this minus h bar square over 2m, we divide both sides by this amount, then we can see that this one here, the alpha and beta is defined as 2m e x over h bar square, and then we take square root. Likewise, beta is 2m e y h bar square, then we take square root. Then we have the solutions: x equal to a sine alpha x, y equal to b sine beta x, beta y. Then alpha and beta, applying the boundary conditions, we have either this one and this one, n and l, they are integers and might be replaced by like nx, l could be replaced by ny, so integers. Okay, alpha and beta, calculate this way, and then the total energy considering the confinement along x and y axis, then we have this one. Then we see that corresponding to each set of n and l, there is distinct wave function depending on n and l. Well, the scale along x-axis and y-axis, let's set to be the same. I mean, the along x-axis, y-axis, Yeah, they happen to be the same. Then we have this equation with certain normalization condition will decide this value, and this is the shape of wave function variation. Then the energy is said to be like this. Look at this. We can define degeneracy. For the above two-dimensional problem, we obtain two quantum numbers n and L. Typically, the number of quantum numbers is identical to the dimensionality of the problem. For a three-dimensional problem, there are three quantum numbers. Look at this. One-dimensional problem, we had one quantum number. Two-dimensional problem, now we have two quantum numbers. For a three-dimensional problem, there are three quantum numbers, as we will see later. Each set of quantum numbers determines a unique wave function. The energy levels for different sets of L and N, however, can be identical. Because look at this, L and N. Let me erase. Let's consider the combination of L and N. It could be 1 and 2, right? Or 2 and 1. But their results are just the same. But this one, we have E12. This one, we have E21. Their energy value is the same, even though their quantum number combinations are different. So these are two different quantum states, but their energy values are just the same. Then we call it, there is degeneracy. This one has the same energy as the corresponding to the case of L equal to N equal to 1. Then we say that degeneracy is actually two different energy states have the same energy value, then we have degeneracy of 2. We have many kinds of problems. That's it for today, but we will keep solving Schrödinger equations for the next 2 classes. Okay, so that's it for today.